Here is the fundamental question behind every machine learning model. Given these inputs and these outputs, what parameters produce them? That question, in its purest linear form, is A times X equals B. A is your data matrix. X is the unknown weights. B is your targets. The matrix inverse, when it exists, solves this in one step. X equals A inverse times B. Today we understand when the inverse exists, how to compute it correctly, and where it appears throughout AI from linear regression to anomaly detection. The inverse of A is written as superscript -1. The defining property is A times A inverse equals A inverse times A equals the identity matrix I. It undoes the transformation. If A rotates or scales, the inverse reverses it. Three conditions must hold for the inverse to exist. First, the matrix must be square, n by n only. Second, it must be full rank, all rows linearly independent, no redundant information. Third, the determinant must be non-zero. A singular matrix has dependent rows. One row is a multiple of another. The determinant is zero and the transformation collapses space, making it irreversible. The matrix 1, 2, 2, 4 is singular. Row 2 is 2 times row 1. You cannot invert it. Let us solve a real system. 2x plus y plus z equals 9. X plus 3y plus 2z equals 20. X plus y plus 4z equals 22. Write this as X equals B. A is the coefficient matrix, X is the vector of unknowns, B is the right-hand side. In NumPy, create A and B as arrays, then call NP, linear LG, solve of A, B. The result is X equals 1, 2, 3, meaning X is 1, Y is 2, Z is 3. Always verify, NP, all close of A times X and B should return true. If it does, your solution is correct. This is the complete workflow. Write the system, form A and B, call solve, verify. One critical practical point, use NP, linear LG, solve, not NP, linear LG.inv followed by matrix multiply. Both give you X, but solve uses LU decomposition internally. It is faster, numerically stable, and avoids computing the full n by n inverse matrix. Only use INV when you genuinely need the inverse matrix itself for subsequent operations. For non-square matrices, which is most real data, use NP, linear LG, PINV, the pseudo-inverse. This computes A plus which equals A transpose times A, all inverted, times A transpose. It gives the least square solution, the X that minimizes the squared error. This is the closed-form solution to linear regression. 4 places the inverse appears in AI. 1. Linear regression normal equations. Theta equals X transpose X inverse times X transpose Y. When the feature matrix is full rank and features are not correlated, this gives the globally optimal weights in one operation. 2. Gradient descent exists specifically to avoid inversion at scale. For a neural network with millions of parameters, the normal equations are computationally intractable. Gradient descent iterates cheaply per step instead. 3. Transformers use softmax as a differentiable alternative to hard selection, no inversion required. 4. Mahalanobis distance in anomaly detection uses the inverse covariance matrix to measure how unusual a metric vector is. Your monitoring anomaly score is a Mahalanobis distance. Key takeaway: the inverse undoes A X equals B gives X equals A inverse B. Use linear LG. Solve in practice. not explicit inversion. The inverse exists only for square, full-rank matrices. Non-square systems use PINV. The normal equations theta equals x transpose x inverse x transpose y are linear regression in closed form. Gradient descent exists because deep networks are too large and nonlinear for direct inversion. 2 exercises. Build the 3x3 system and solve it, then derive the shape of each term in the normal equations for a 100x3 data matrix. You now have the complete linear algebra toolkit for reading ML papers, vectors, operations, dot product, matrices, multiplication, transpose, symmetric matrices, and now the inverse and linear systems. Video 11 opens the door to something deeper: determinants, what they tell you. Subscribe so it is ready. Drop the normal equations for linear regression in the comments, theta equals, and show every shape. See you in video 11.